My name is Vladimir Kolesnikov, and I'm going to give the presentation about PBXT or PBXT for sure, storage engine for MySQL that we developed, Primebase, and to talk about it in the context of the technology trends, current hardware technology trends that we believe affect the database world and affect you as a DBA or database developer. So more specifically, first of all, I'm going to give you a short introduction to the PBXT feature-wise, just to point out most important things that PBXT can do. Then I will talk about the trends and the trends that we recognize and believe affect the database, the database world the most, from the performance point of view, and next I will talk more specifically about how our engine implements, how our engine architecture is built around those trends. Or next I will talk about some more specific topics like in-memory tables implementation and the tools that you can use, also our tools and common MySQL tools that you can use for PBXT PBXT performance monitoring. Then I will present some benchmarks. These are not the latest benchmarks, but they can give you a picture of where we are. And then I will give some general information about where you can download it and so on. So, first of all, it's a pluggable engine for MySQL 5.1. The development was started for 5.1. Then it was also ported, so to say, to 5.4, to Drizzle, and to MariaDB. So it's available for all these products. It's open source. It's GPL2. It's also could be available, I guess, under other licenses, as the Primebase is the only owner of the whole code base. It's transactional. It supports the normal MySQL transactional syntax begin and rollback. It's ACID compliant. It supports, talking about isolation levels, it supports level between repeatable read and serializable. So it's not strictly speaking serializable, but because otherwise you would just have to serialize your transactions. But it has a level that enough for taking consistent snapshots of your database, so you can just start a transaction and read out your database into file or into script. I mean binary file or script, and that's it. In other words, it doesn't permit phantom reads. It supports row level logs. If you were present on the earlier presentation by me or by Paul McCallum, who is, by the way, the author, the original author of the engine, you could hear that we had some special row locking model, like there is a fixed amount of logs per table, say 1,000, and every 1,000th row is logged by the same log. But this model worked well on small scale, but as we started to try the engine on a larger scale, we decided to throw it away and implement true row level logging. So now every row has its own log. Referential integrity is supported as it's implemented by MySQL. I mean, by MySQL, the full MySQL syntax is supported, including no action, which is not supported by some engines. The engine implements fast rollback and recovery. What this means? This means that usually in other engines, for example in InnoDB, you have so-called undo log, which means that whenever your transaction rollbacks or you do a recovery and have to roll back that transaction, you have to overwrite your data. This is not needed in PBXT. What is done is just all uncommitted data becomes a garbage, and it's utilized later by background threads. And finally, it's available on, I would say, all major platforms: Linux, 32 and 64 bits, Solaris, OpenSolaris, including Intel processors and Spark, BSD, MacOS 10, and Win32. Basically, Win64 is also almost supported. The only problem is that Microsoft Compiler doesn't support inline assembly in 64-bit mode, so we would have to implement some minor pieces of code which are currently, for performance reasons, are implemented in assembly, just using C and Windows function calls. That's it. So you can see from this short description that this is a common purpose engine, and you might want to ask, well, what's the difference? And well, to answer your question, once I had a talk with one of MySQL developers, and he pointed out that databases are not also about performance, they are only about performance. In the sense that, of course, you want to have some things, to see some things as given, for example, reliability, data consistency, and from things that you really evaluate about databases. Performance is number one, and very often is the only. So if your database is twice faster than the other one, then user is going to use it. Or if you are a user, you're going to choose the one that runs fast instead of the slower one. So it is important, and in order to achieve acceptable or optimal performance, you have to utilize the hardware, the currently present hardware. We target, so to say, commodity hardware, and we recognize the following three major trends in current commodity hardware. First of all, there is no more increase in CPU speed through increasing frequency. I have a nice graph on the next slide. As somebody said, the free lunch is over. So you could see that since day one, the frequency of CPUs was increasing, and it was doubling every 18 months, according to the very well-known law, till 2006. And since that time, you can see that it not only didn't increase, but it also decreased. So this is what I mean by saying that free lunch is over. You can't just replace your hardware every year or something and get better performance. You have to really have the software that can utilize multi-core systems to scale well. And CPUs not only becoming slower in terms of megahertz, but also becoming simpler. The one clear example is Intel Atom architecture, which is basically a cut down from their Pentium architecture. It has smaller cache, has thrown away some advanced techniques like speculative execution and so on. And there are even companies that try to build, or maybe have already built by this time, enterprise server systems based on Intel Atom. So you can see what are the trends. I return to the previous slide. So what does this mean? This means that your software have to log very smart. Your logs should cover as little area as possible, and the other side is to split data that you operate. For example, if you have a list, you have to split into hash map and have individual small lists, so that if two concurrent threads access data, there is high probability that they will hit into different lists and will log different lists. this one side of utilizing multi-core CPUs. The other side is to split processing between several threads. Historically, MySQL in MySQL, a query is processed by a single thread, and there is little engine developers can do about this. I mean, you can't select several rows in parallel threads, in concurrent threads. That's just impossible. MySQL currently doesn't allow that. So what you can do is to minimize processing in foreground of MySQL requests and do as much as possible in background threads when user is not waiting for you. For example, if you have an insert, you have to save quickly data somewhere and defer writing to disk to background threads and let user thread go like this. Another trend is that CPUs currently are 64-bit, and which means they have huge address spaces and you can install a lot of RAM. So you have your engine has to be able to scale well. This means it doesn't mean that it should require a lot of memory, but if there is a lot of memory, it should be able to utilize it. It means that it should use smart application technology, smart application algorithms, buffer data, and again defer processing to background threads. And the last, but not the least, is solid-state drives. For solid-state drives, how they are different from normal hard drives. There is first of all no random access penalty. You can read data randomly almost as fast as you would read it sequentially. I say almost because most of the drives do some have some uncontrolled cache and do some pre-caching, prefetching of the data, and of course if you fetch several blocks, they will prefetch the next blocks, and of course further fetching of these next blocks will be faster than selecting something randomly from other location. But the idea is that the reading from drive itself doesn't require some repositioning of heads or a similar operation that takes a lot of time. What this means? It means that no clustering is needed. What's clustering? Well, just to refresh quickly, or what we understand by clustering, is ordering data physically by some pattern. For example, very often, or in indexes, index B3 is a typical example of clustering. In index, your data is clustered. I mean, in indexes that hold the values of keys. For example, in InnoDB, all the data in table is clustered by the primary key. All the rows make a huge B tree. So all the table, it's not just a flat list of rows, it's a huge tree. And of course there are secondary indexes that cluster by specific, by other fields. This is not needed anymore, or is not that effective anymore as it was with hard drives, with solid-state drive. But what's important to remember about solid-state drives is that you still have to write sequentially, as writing randomly has some problems. As far as I know, it's particularly because of the thing that I already mentioned, of the caching, because on the hardware level, to write a block on solid-state drive, you have first to read the block and then modify it and write back. So if you write random sequentially, you can again pre-cache data on controller and make the process much faster. But I don't know, maybe it's not the only reason. I don't have much details about this. What I know is the result that random writing is much slower than sequential. So these are the three things that we try to build our performance around, our architecture around, to achieve maximum performance. maybe you could have a question like, what about normal HDDs and whether PBXT has acceptable performance on normal HDDs. Yes, it has, and I will show you some benchmarks to give you an idea about PBXT performance. So, but of course, the maximum performance can be achieved on solid-state drives. So, the major points of PBXT engine design. Write once, log-based. What this means? It means that the data, or speaking precisely, most of the data is written only once. In InnoDB or in other engines, you first write data to the transaction log. This is done quite quickly, and then on commit, your data is moved to table. So the data is written twice, which of course much slower than single write. In PBXT, this is different due to log-based architecture, which I will explain a bit later. Most of the data is written only one. More specifically, all heavyweight data, varchars, blobs, text fields, and so on, is written only once. Next feature is disk-based MVCC. MVCC stands for multi-version concurrent control. It basically can have two implementations, memory-based and disk-based. We use disk-based MVCC because otherwise you lose scalability. Once your memory is filled with your record versions, you freeze. You can go. Fast commits, I already talked about this. No, sorry, what was different. Fast commits means that you don't synchronize table and index data on commit. You have your data in logs, and for example, unlike again other engines, we don't synchronize indexes on commit because indexes don't contain unique data. They can be recovered in case of crash from the transaction log. So there is no need to lose time on commit to write indexes. The same is true for the table data. There is no need to write data into tables as could be recovered from transaction log. No in-place updates. In-place updates cause a lot of small and big issues, so the decision was made to not make in-place updates. This means that whenever the record is updated or deleted, a new version of record is created and written, and a row is basically a list of record versions. And something that I already mentioned is that when I talked about fast recovery, is this can be done due to no in-place date, due to creating new version every time the new version, the record is updated, the row is updated. Again, thanks to this, we have no undo. And yeah, the last thing to remember or to know, to keep in mind, is that there is file per table. We believe that table spaces are not very efficient. So, I mean, in what sense not very efficient? In the sense that having file per table, you can better control your database from the performance point. You can split it, put individual tables into different hard drives, or maybe on NFS. No, I'm not sure NFS is possible because it doesn't support locking. Yeah, but at least you can put it on different drives or put different folders and so on. So it just gives you better control over your database. On this slide, you can see the data format of the format in which PBXT stores data. Basically, there are three parts. First, the raw index file. This raw index file is simple list of pointers into table. Basically, every of these pointers is a pointer to the most recent version of the record. And in handle data file, as I already said, you have a number of record versions, and every record version has a pointer to the previous version. The data itself is split in general case into two parts. The handle data file keeps small fields that you usually would use to search data, while data log file and the fields in the handle data file are always fixed size. And data log file contains all the records that doesn't fit into handle data file. So the idea is that when you search for the data, you would read information from the handle data file most of the time, and in perfect case. This data has fixed format and usually small, like some integer fields, keys, dates, and so on, such small fixed data. And all data like varchars, blobs, and so on goes that you don't really use to search data. I mean, if you search by varchar, you usually create an index and use index, not the data itself. So it goes in data log and is read only when you really need to return it to user. That's basic idea behind the data form. Insert, update, delete. In red border, I marked the files that are affected immediately by these operations, by data modification operations. Basically, as I said, due to load-based architecture, we write the data to our log files, to the transaction log file and to the data log file. What's important about this is that data is written sequentially. It's never written randomly, because it's logs. Data is just up and up all the time. The raw index file and handle data file are not affected. They are then modified and synchronized by background threads. So we defer processing. Select. Select reads from raw index. Basically, I already gave some description of how data is retrieved. First, by the raw index file, you find which row you need if you're doing table scan. Then you read handle data file, and the engine detects which fields are really needed to the MySQL, and either retrieves the contents of the handle data file, or if needed, also reads the data from the data log file. You may ask whether data log file is always present. No, it's not always present. It's optional. It's created only when there is something to put there. If there is nothing to put there, for example, if you have many-to-many relations table with keys, which contains two integer or whatever size fixed fields, then you will have only handle data file for that table. And what is important also, what I didn't mention, is that in that case, the data will have format which is native to MySQL. So there is no data translation is made. The data is just read from the disk and the image is returned as is to MySQL, which is also very fast. So you may ask how data gets from log files into raw index and handle data files from where it's finally read. Oops. 5 more minutes? No.
Just 10 minutes.
Okay. There are 4 background threads that move data between various files. I will try to illustrate. Basically, there is writer thread. It works in background in periods of time when there is a relatively low activity, or the in-memory cache is more or less filled, then the writer is also activated. forced to be activated. So what it does is just reads transaction log and writes data to the table files. Quite simple. What's important again is that it's down on the ground, so user is not waiting for this to be done. Sweeper. Sweeper, you remember we have a list of versions. For example, transaction T1 starts and reads some version of record, say version 1, and then another transaction T2 starts and updates this record and writes version V2. Then transaction 1, when transaction 1 still runs and does again a select, it still sees the version that it has seen initially. That's guaranteed. But when the transaction finishes, the first transaction T1 finishes, the first version of the record is not needed anymore. It's not visible by any transaction and it's not needed. And it's actually the work of the sweeper thread to take care of these records and to mark them as free and be reused by the other transactions.
Would have to sweep the entry to the data log file as well?
No, that's done by yet another thread. I will talk about that. Checkpointer thread. As I said, the data is not synchronized to tables and indexes on commit. Still, if you don't synchronize for a long time and you get a crash or you get power failure, on restart you will have to reread the transaction log, to replay the transaction log to recover your data. And what checkpointer does is it makes sure that data till a certain point is already synchronized to table and index files. So in case of recovery, you will have to start not from the beginning of the log, but from the last checkpoint. Checkpoint is done after recovery on startup, it's done on shutdown, and it's done periodically during engine operation. There is a variable that controls how much data should be written in the transaction log, not shown here, in order to be for checkpointer to synchronize the data to this. And answering your question, there is a compactor thread which takes care of the record tails which are not used anymore. In difference to data log file, the entries in the to the handle data file, the entries in the data log file have different sizes. So it's hard to reuse the place which is not used anymore. Instead, what we do, we do not reuse gaps in the existing data log file. Instead, we create a new data log file. All data log files have the same size, so we can reuse, not delete, but just save and then reuse all files. We just rename them and move all valid data record tails into the new file. What's important is that this process is very unintrusive, I would say, into operation of the engine as such, because while it's in progress, the data doesn't need to be logged, because it doesn't matter whether the thread reads data from the old data log file or from the new. It's valid. Once the pointer has been changed, it points to a valid record. If it hasn't yet been changed, it still points to a valid record. And only once this operation is fully completed, the file is utilized, I would say, not removed, but utilized. Later it's reused, so because it's faster than deleting and then allocating new file. So that's basically about the architecture. I hope you got the general idea of what happens inside the engine. If you have some specific questions at this point, I will be happy to answer. If not, I will talk about specific features. One specific feature that we have is a memory table. Basically, it's the same table as normal PBXT table, but instead of disk, the data is stored in memory. Why another in-memory table? You know, we have a so-called heap engine or memory engine, but there are several problems with this engine. It's not transactional. It has table locking. I mean, table level locking. It doesn't have row level locking. So it's not scalable.
It doesn't support blocks.
Yeah, right. Doesn't support blocks. So to address these problems, we have created the in-memory version of the PBXT engine. It supports ethnicity, consistency, and isolation like supported by the normal PBXT table, and even durability can be easily added by just saving and synchronizing on commit the transaction log, because the transaction log is still written. All we need is just, for the memory table, we have just relaxed the requirement of durability. We don't synchronize it on commit. Just written somewhere on the ground, we don't care about it at all. But if for some reason we would need durability, that would be easy to implement by simply.
Does it contain indexes in the memory as well?
Yes. And all the blobs and all the data log file data is in memory as well, so all the data is in memory. It can be, what's also important about this table is it's a normal PBXT table in the sense it can be combined with other on this PBXT table, combined from point of view of transactions. For example, a very common usage for in-memory tables in general is to keep some calculations in memory for quick access, some summaries, totals, and so on. So whenever you modify your table and then roll back, you want that your new value also be rolled back from your in-memory table. That can be done automatically with no special effort is needed. Also, you can have foreign keys that involve in-memory tables. That's all done normally, no special effort is needed. It supports blob data, unlike the storage engine. And the syntax to create, we reuse. So as far as I remember, this is standard MySQL syntax. It's from cluster, I guess. We just reuse it to have nice syntax for creation. PBXT performance monitoring. So we are over with in-memory tables. Just a quick overview. There is information. IS stands for information schema. So in real life, it's not IS, it's information schema. .pbxt statistics table, which is a plugin for MySQL information schema, and it keeps performance counters, 48 performance counters for various parameters of the engine. What's important is that the performance is collected by thread. And then, when you do a select, the information schema plugin gathers everything together into a single result. This is needed in order to make accounting performance as intrusive, as little intrusive as possible from performance point of view. Because, for example, performance counters that exist in MySQL, they use logs. So whenever you want to implement something, you have to log some log and then do your operation. This is not, we do not do this. We keep all the statistics per thread, so it's very fast. It doesn't affect.
Your time is up.
Okay, yes, time is up. So if somebody wants to read, if not, if you're interested, we have XT tool because it's the last session. I mean.
Well, we have to close the room if there's the barbecue going on.
And people have to eat and...
Okay, then XT2 and so engine PBXT status. You can learn more online. PBXT statistic tables, one time. Just several benchmarks that I wanted to present. This is quite old, maybe several months old benchmark. This is the standard toolsys bench, which is run on OLTP read write workload, 10 million rows on SSD drive, on 8-core machine. You can see that InnoDB version 103 starts to, its performance falls down right after the number of cores is reached, while PBXT is still increasing performance for some time as number of threads is increasing.
No, you put me back.
This is a single threaded scenario. Huh?